सो वेलकम अगेन। आप सभी का एक बार फिर से स्वागत है हमारे यूट्यूब चैनल फिजिक्स क्लासेस पर। इन द प्रीवियस लेक्चर वी डिस्कस्ड थेवेनिन थ्योरम एंड नाउ टुडे our topic of discussion is Norton's theorem. So far we have discussed first we discussed superposition theorem, then we discussed Thevenin theorem, and today yet another important theorem in electronics is the Norton theorem. So similar to Thevenin theorem, Norton's theorem also reduces one complex network to a simple equivalent network. And as you can see in this diagram, there is a circuit shown as a box, means it contains so many sources, current sources, voltage sources, and some resistors. And in the right side you can see the Norton's equivalent circuit. So as it is clear from this diagram, this Norton equivalent circuit consists of a current source IN and a resistance Rn in parallel with the source, and the load terminals are open. Any resistance could be added here, and we can just calculate the amount of current or voltage drop across this load. So we will also compare this Norton theorem with the Thevenin theorem, as there is hardly any means there is both are almost similar. The difference I will point out. Okay, so here we have let us define what is the value of IN and Rn. In Thevenin theorem we had VTH and RTH, and here we have IN and Rn. So this Norton equivalent current IN is the short circuit current between the two output terminals in a circuit. So here you can see the A and B are the load terminals, output terminals, and this IN will be the short circuit current, means when this A and B are short circuited, means RL is removed, any load is removed, and it is just short, then the amount of current which will flow through this AB will be the IN. Okay, and in Thevenin theorem just we did just reverse, means we calculated the open circuit voltage through the load. Here we will calculate short circuit current between the load. And what will be the value of Rn? The resistance will be in parallel with the source. Just like RTH, the Norton equivalent resistance Rn is the total resistance appearing between the two output terminals or the load terminals, with all sources replaced by their internal resistances. So this step is just like the we did in Thevenin theorem. Nothing is different here. We will just open the load terminals, and from that side, means we will look back from the load terminals, and we will determine the total resistance of the network, when at the same time all the sources will be removed and replaced by their internal resistances. In case of no internal resistance is mentioned, we will replace a voltage source by a short circuit, means zero resistance, and a current source by infinite, means open. Let us see what are the steps to find out the Norton equivalent circuit. First step is short the two terminals between which you want to find the Norton equivalent circuit. Determine the second step is, then we will determine the current IN through the short terminals, means the output terminals. Then after that we will find out the Rn, the Norton resistance, equivalent resistance between the two open terminals, with all sources replaced with their internal resistances. So Rn and RTH are the same because the process is same. only difference is the finding out the VTH and IN. These are the two difference. Then after that, once we find out IN and RN, then we will connect IN and RN in parallel. That will give us the Norton equivalent circuit. Let us understand this by using an example. So here we have a circuit. The circuit is given with the 5 volt voltage source and 47 ohm, 100 ohm, 47 ohm and RL. A, B, RL is connected between A and B. This is the load resistance. So if we are asked in this question, you can see we are asked to find out the IN only right now. But it can be asked, the complete question is we have to find out a Norton equivalent circuit for this circuit. Okay, so what we will do, first we will find out IN, then we will find out RN. So let us see. For finding out IN, first we have to just one second. Yeah, now I can draw here. So for finding out the IN, the amount of Norton equivalent current, we will, you can see here I have pointed out this is the load or the output terminals A and B, and RL is connected here. So we will first remove it, means it will be short circuit. It will be connected without any resistor, direct through a wire. So A and B will be short circuited, and then we will find out the total current. For finding the total current, what we will do, we have this 5 volt voltage source, IN equal to V upon R, okay, from the Ohm's law, and V is the 5 volt, and R we will find out by the combination of these R1, R2 and R3. So you can see R1 is in series with the parallel combination of R3 and R2. So R will be R1 plus R2 parallel R3, simply. Okay, so let us see what happens. So here I equal to V upon R, as I wrote in the previous slide. Then here it is written as RT. Okay, so then IN will be this Vs upon RT. This RT will be R1 plus this one, R1 plus the parallel combination of R2 and R3. Okay, so it will become 47 plus this combination, it is coming out as for 79 ohm. So I will be 5 volt divided by 79 ohm, which will be 63.3 milliampere. So again I request you to not just rely on these data while going through this lecture, but also try to calculate the values, whether these are correct or not. So then IN will be, okay, so far we have calculated the total current flowing in the network through this source from here. This is termed as IT. Okay, so IN, what will be IN? IN will be this current. Okay, one second. This is the IN as pointed out here from this. So this IN will be same as the current flowing through this R3. So current flowing through this R3, once we have calculated IT, total current, this is the IT is this. Then how this IT will be distributed from here? One current will be going here and one current here. So we have already discussed it, how the current is distributed and divided in a parallel branch of resistors. So if we are concerned we are for calculating the current through this R3, then this will become 47 upon total 100 plus 47, means 47 divided by 147 into the total current. Okay, the resistor which you want to calculate, the resistor, the current flowing through that resistor will be in a parallel combination, will be the current total current multiplied by the ratio of the resistances. So here you can see IN will be this one, total current IT multiplied by R2 upon R2 plus R3, means 47 divided by 147, and this is coming out as 20.2 milliampere. This is the IN. First thing is done. Now second thing is to find out RN. Now let us see how to find out RN. So for RN we will just, as we used to do for Thevenin theorem, we will calculate this total resistance of the network when we will replace this. Okay, when we will replace this voltage source, one second. Okay, now here this is the voltage source. This will be removed and replaced by a short circuit because its internal resistance is 0, and then these A and B RL will be removed. These are open terminals, and we will calculate the total resistance of the network from this direction, as looking back from the load terminals. So this will be R3. R3 is in series with the parallel combination of R1 and R2. Here we have plotted here. Yeah, this is the diagram. A and B are open. Vs is replaced with a short circuit, and total net resistance of the network will be R3 plus R1 parallel R2. This will be Rn. This is same as RTh. Thevenin also, both are the same. So this will be coming out as 100 plus, because R1 and R2 are same, so it will be R1 by 2. 100 plus 47 by 2, 124 ohm. Okay, so we have calculated the values of Rn and In. Now we can draw a Thevenin equivalent circuit. Sorry, not Thevenin, it's Norton. It's Norton equivalent circuit consisting of a current source In here and Rn in parallel. So if there is any load given between the A and B, load resistor RL, and we are asked to find out any current or voltage drop through it, then it is now easy. Now let us see another problem, numerical problem, which we will try to solve it first by using Thevenin theorem, then by using Norton theorem. So question remains same. We will use on a single question, but we will use two different methods. One is Thevenin, another is Norton, and we will show you, I will show you that we will get a same result, and that also proves the equivalency of these two and validity of the theorems. Okay, here we have this is the circuit. Okay, here is this, we have the circuit. This is the circuit consisting of 36 volt source, and 12 ohm is the RL, means load resistor. 3, 4 and 6 ohm, these three are the making the network, our electronic components. So this is the circuit, and what is the question? Let us see here. The problem statement is calculate the current flowing through the 12 ohm resistor using Norton's theorem. Okay, first we will calculate it using Norton, then we will calculate using Thevenin. So first, just as we discussed just minutes before, first we have to our goal is to find out Rn and In. Okay, In and Rn. So what will be the In? For In is the short circuit current. So here in this circuit, what we have done here, we have just removed this 12 ohm resistor, and this current, whatever current will be flowing through this terminal A and B, this will be ISC or In of short circuit current or the Norton's current. So this will be same for finding out this current. We will find out the current flowing through this 4 ohm resistor. Whatever current is coming from here, it will come at point C, it will divide into two different parts. We are interested in finding out the current flowing through the 4 ohm resistor. So first let us calculate the total resistance of the network as looking from this side, from the source side. This will be V upon R. V is 6 volt and R is series combination of 3 plus 3 is in series with the parallel combination of 4 and 6. Okay, so 3 plus 4 parallel 6. This is the total resistance. So it will come out as 3 plus 2.4. So it will be 5.4. Here you can see 3 plus 4 parallel 6, 5.4. Current will be 36 divided by 5.4, which will be 20 by 3 ampere. Okay. Now this is the total current. Okay, this 20 by 3 current is the current coming from here. Now how it will be divided? Because we want to calculate the current flowing through 4 ohm resistor, 4 ohm resistor only. So it will be 6 divided by 6 plus 4 as written here. 6 divided by 6 plus 4. This is the short circuit current into 20 by 3. Total current is this, and it will be divided in this ratio. So it will be coming as 4 ampere. This ISC, this will be IN. ISC or IN are the same. Second thing is to find out the Norton equivalent resistance, which is Rn. So for this we will remove the load. These A and B terminals are open, and we will look back from this terminal. From this direction, as we see, the total resistance will be 4 ohm plus the series, means parallel combination of 3 and 6 will be in series with the 4 ohm. So 4 plus 3 parallel 6. Okay, as written here, 4 plus 3 parallel 6. 3 parallel 6 will be 2, and 4 plus 2 will be 6 ohm. This will be Rn. So how our Norton equivalent circuit will look like: a current source In of 4 ampere and a parallel resistance of 6 ohm, and load terminal contains load resistor 12 ohm as given in the initial or original circuit here, 12 ohm. So now we can calculate the current flowing through this 12 ohm resistor. So 12 and 6 will be parallel. Okay, total current, because now we are not dealing with the voltage source, so total current is coming as 4 ampere, and this current will be divided here and here. Again, if you are interested to find out the current flowing through 12 ohm resistor, then we will write at 6 divided by 6 plus 12 into total current 4. So it will be 6 by 18 into 4, which will be 4 by 3, or the 1.33 ampere. This current is the current flowing through this 12 ohm resistor IL. Okay, this is the answer. Now let us see whether the same result we will get using the Thevenin theorem or not. So remember it, the final result current flowing through the resistor is 1.33 ampere. 1.33 ampere. Okay, here this circuit is same. Now we will use Thevenin theorem. So for Thevenin theorem, what we will do, we will have to find out first VTH. VTH is the open circuit voltage. Okay, open circuit voltage between the load terminal. VTH. So VTH, we will remove the 12 ohm resistor, and now you can see here, this is the VTH. Load terminals are open, and because these are open, now the current will not flow through this 4 ohm resistor, and current will only flow, because 36 volt is here, current will only flow through this 3 ohm and 6 ohm. So it is very easy to calculate the total current. 36 divided by 6 plus 3. Okay, so 36 divided by 9 means 4 ampere. 4 ampere will pass through this from here. 4 ampere will pass through this. And how we will calculate VTH? VTH is here. This is the VTH, Thevenin equivalent voltage or the open circuit voltage. So it is same as the, because in parallel combination potential difference or voltage is same. So VTH is same as the voltage drop across 6 ohm resistor, this. So total current is 4 ampere and 6 ohm voltage drop will be 24 volt. VTH will be 24 volt as written here. Now how we will calculate RTH? RTH as we just calculated in Nortons, because RTH is equal to RN, we will just use this. Load terminals are open. As looking from this side, 4 plus 3 plus 6, 4 plus 2 will be 6 ohm. How we will draw the Thevenin equivalent circuit? This is the Thevenin equivalent circuit, consisting of a voltage source of VTH 24 volt and a resistance of 6 ohm in series. Okay, note down that in Thevenin we use the two difference in Thevenin and Norton is, in Thevenin we calculate open circuit voltage between the load terminal. In Norton we calculate short circuit current between the load terminals. Second difference is, in Thevenin we connect a series resistance in series, but in Norton we connect a resistance in parallel. Okay, so here VTH is 24 volt, RTH is 6 ohm, and load terminals load resistor is 12 ohm RL. So the current will be flowing through this 12 ohm will be 24 divided by 6 plus 12 as written here, 24 by 18 will be 1.33, as the same result which we obtained using the Norton's theorem. So we have proved here that same question can be done using Norton's theorem as well as Thevenin theorem. We can also use Kirchhoff's law to find out the same result, and this will be your home assignment. You can do it. You can check whether using Kirchhoff voltage law you are getting the same result or not. So far we have discussed 3 important theorems, and another theorem we will discuss tomorrow, which is maximum power transfer theorem. Thank you.